So for the final exam, you should expect one problem at a minimum dealing with water or other liquid. You can handle other liquids, although water is the common liquid, right? You could, where you have a piping system, you have a pump, where you could have your major losses and the minor losses. You have a fitting or something. So you just need to either size the pump, select the pump, something. Get a system curve. We talked about the pump curve. Talk about different styles of system curves, shapes and behaviors. Talk about the operating point. Talk about net positive suction head calculations. Making sure that you're not going to have a problem with cavitation. So that's all in there. What's the second area? The heat exchanger, but not the compact. I don't have the whole time just to give you one problem with a compact heat exchanger like we did before. Just traditional, so it's not compact. It's just a traditional heat exchanger, okay? So things like log mean temperature difference, come on, I can do that, LMTD. Things like sizing it to get the area, rating it to get the Q, get the U, the overall heat transfer coefficient. 3, we talked about air systems, and I'm going to spend some more time on it. This is a water system, here's air system. Instead of a pipe, what do we have? We have a duct. Instead of a pump, what do we have? We have a fan. And we still have losses. You still have major losses. You still have minor losses. You still have straight runs, and then you have fittings. So put that together with this fin. You still have your affinity laws for the pump, liquid system, the same. Affinity laws for the fans. Fans can be a little more complex because you have little slightly different characteristic, especially you have forward tip blades on blower motors. And then what was the last one? Uncertainty analysis. And you can do the differentiation, or you can do the not differentiation, you can do the perturbation. So you asked me to solve a makeup problem. Who would like to give me a problem where we're going to use R for the response as a function of, let's do it either 2 or 3 inputs. We don't want to do too many inputs, right? And I have to be able to either differentiate it, that's the hard part, to pick a function. Anybody want to contribute one? If you contribute, you have to be able to differentiate it. Pardon? We'll definitely have something with the x to at least a power. So in x1, our function, I'm trying to just write it out. Let's put a constant a plus a constant c times x1 squared. We have to have another variable x2, and let's do the sine of x2. This is probably not a very good function, but hey, I can write sine, S-I-N. Does that make sense? Here's a plus a constant times x1 squared times a sine of x2. For each of those inputs, x1 and x2, I have x1 mean. There's different ways you can write that. You can write it as x1 with a bar, or x2 with a subscript, additional subscript for the mean, x2m or x1m or x1. You prefer x1 mean. Plus or minus, you have the uncertainty in x1, the uncertainty in x2. Okay, I'm going to pause. How can you solve that problem? I want the mean response. That's the easy part. You should at least get 50-50 on that one, right? That's easy. And then the uncertainty in the response. One of the methods is the traditional method. And so both of them have the the mean response is simply the function evaluated at each of the means on the inputs. So you just take A and the C and you put x1 mean right there and you square it and you put the sign of x2 mean. It's the same for both of those approaches. But the other approach is going to say, I want to find the uncertainty in the response. That's the hard part. So I know it's a summation of some terms, and then I take the square root, and each of those terms are something squared. Remember the formula? Isn't it the partial of that response with respect to each of the inputs, one at a time? So we'll put I here, and we'll sum over all the i's. And after we take the derivative of that response with each of the inputs, I'm going to have to evaluate it somewhere. Evaluate it at the mean, just like we evaluated the response at all the means of the inputs. You evaluate the derivative at the mean. And then you multiply that by what? The uncertainty in each of those inputs, x of I. And so you would say, okay, for this problem with two inputs, I have to get the partial of that response with respect to x1. What is that value? C times 2 times x1 times the sine of x2. And then I need to get the partial of the response with respect to x2. That's going to be what? C times x1 squared. You're good, cosine 2. And so now I just stick in the mean values to get that derivative evaluated at the mean, get that derivative evaluated at the mean, and I have some number. I have a number for those. And then I multiply by the uncertainty, square them, sum them up, square root, and that's it. All right, what about the sequential perturbation method? You almost just write it out like you're doing it in Excel. So you would say that my x is 1 has a mean value, put the mean value here, and then you have plus or minus some uncertainty. Maybe I should put it like this: x mean and uncertainty, and then this is x1, and then that's x2. All right. All you do is come down here and you get the response evaluated at that using those means. All you did was get r sub m right there, just like this is r sub m. Okay, then you come over here and you're going to have only a 2 by 2. If you had a 3 by 3, it would be 3 inputs and you have a perturbation matrix of 3 by 3. And so what is the value of x1 in this 1, 1 part of the matrix? That would be, maybe I should throw some numbers here. I mean, or does it follow? I mean, if this is my function and I said x1 is equal to 2 plus or minus 0.2 and x2 is equal to, maybe you should put it in radians, I don't know, 1.6 plus or minus 0.3, right? Well, then I would have right here, I would have my 2 and my 1.6, and I would have my 0.2 and I'd have my 0.3. Right? And then to get those to evaluate r sub m. That's easy. Then right, what's here? Wouldn't it be 2.2? And this is 2. And this is 1.6. Then 1.9. And then I use the same function to get this perturbed r, and the same function to get this perturbed r. I mean, we can run numbers if you want to run them. And then what do I get? A lot of times I'll do the difference in the r. So I'll get this r perturbed minus r mean. That's this one minus that one. And I'll put it right there. And I'll have also r minus r mean. That's the r that goes there. So I calculate those differences in r. And then maybe I even do additional step, r minus rm square it, r minus rm square it. Then I add those together, take the square root, and that is my uncertainty in r. the uncertainty in R is the square root of the sum of those. Any comments? Maybe we press forward then into air system. Okay. So now we want to go and talk a little bit more about the air systems. It's a lot like the water system, but it's a good review for water systems is when you cover air. So the air system, what is a typical problem? Think about your house or apartment or someplace. You have multiple rooms in it. You could make a room a zone. Or if you have a big building, you would have multiple rooms kind of clustered together in zones because you expect their thermal environment to be the same, the loads in that place. But you bust up your house, your apartment, your building into zones. So you can just do a one-dimensional, let's say I have a hallway down here, I have offices, some big conference room, something with equipment, photocopiers and other pieces. So the buildings aren't all the same. Sometimes you have interior space, sometimes the exterior space. If this is the south, then this is the east, and this is the west. Believe me, that west in Texas is going to be the brutal side from noon on in August, right? So then what you do is a load calc. What's that mean? You find out the hottest day in the summer and what is Q getting in that I have to remove, and how are you going to remove that Q? How do you remove heat that's in this room? You remove it by dumping in cold air. That's how you remove it. So you say that I want to maintain that zone. Typically it's 75 degrees F at 50% relative humidity. Get the temperature before the humidity. If you're at a museum, you got to control the temperature and humidity. You're a hospital, you got to control temperature and humidity. There's some places you got to get them both right, and that's going to cost a lot to maintain and operate that piece of equipment. But typically it's just get it to 75. How many people want it lower than that in the bedroom that they sleep in? Yeah, most hands are up. So it needs to be like 70, and I've seen some people, I want to sleep in 68, and something like that, right? So anyway, you pick the zone temperature that has to be controlled at, and you design for the worst day to get it there. I'm thinking of summer, and I'm thinking of air conditioning. And so what is the temperature of the supplier? You can't dump in, negative 10 degree F air. That's just not feasible. So what are they going to dump in? Basically 55 degree F air. Oh, you can wiggle that around a little bit, but so numbers just come around and around that you're going to dump in 55 degree F air. So now it tells you how much heat you can remove based on the flow rate. Isn't it? Isn't it the mass flow rate times the specific heat times the change in the temperature? Isn't that kind of, you're bringing in cold, taking out hot, isn't that the heat removal with the air? Because what temperature is the air that after it comes in at 55, mixes well, and it goes out? What air temperature goes out? 75 or 70, that's what it goes out at. So that delta T is the temperature out minus the temperature in. Typically, we got a 20 degree delta F. And then the specific heat of air, 0.24 BTUs per pound degree F. You have the density of air, 0.075 pounds per cubic foot. These are 0.24. What is it? BTUs per pound degree F. This is typically 20 degrees F. If you have different design conditions, that's fine. What is the air density? 0.075 pounds per cubic foot. And what does that leave you? The volumetric flow rate. Maybe I should have used a different symbol because Q is often used for the volumetric flow rate, isn't it? And maybe lowercase q is the heat removal or the load. So what does this dictate? How many CFM of that air I need to get to that room? So you sit there and you say, you know what? I need to get to this square footage 150 CFM. I need to get 225 CFM over here in this zone, in this room. I need to get 400 CFM. I need to get 180 CFM. I need to get, what you see what we're doing? You took your load calcs, you knew your supply, your room temperature, your zone temperature, you basically figured out how many CFM of that conditioned air I'm going to need to dump in that space. Well, where's my mechanical room? Mechanical room's right here. All of that air has got to get back to the mechanical room to get conditioned, and then when it's conditioned, it has to come out and be dumped into the space. It is not rocket science. You say, what type of ducting do I want? And it's kind of like, remember the reverse return and the direct return on the water piping system network layout? The same thing. Maybe you just say, I'm going to come out with a main duct trunk, come down this way with a main trunk, and then off that main trunk, whoops, that erased some of that. I'm going to dump off with dump off a little, bring them off, right? And people like to install flex duct, but if I was you, I was buying a new house, I wouldn't let them do it. But everybody's doing it. You know what I'm talking about? You ever been up in an attic, looked at flex duct? It doesn't stay around very long. They take it over a rafter run, and what does it do? That round kinks pretty poorly. Think about the airflow through that. You think that's uniform cross-section? Give me the old fiberboard duct. And that's what they used to all be. And you can even see the people still cutting it and installing it, but it'll be rectangular duct and it'll be fiberboard. You can't really clean it as well, but they have other stuff. You talk to your builder, you're going to be rich. You want the house that you want, not the house you're going to settle for. You get the duct system right. You get the windows right. You get the exterior sheathing right. True? Tell them, no, that's west facing. I want a decent overhang on the awning and stuff like that. Whatever, you were home. But anyway, we're going to get this, the flow rates to each place, and we have a general layout, and now you can just do the math. It's pretty simple. Let's see, if I need 225 coming CFM, how much in that run right there? 225. And then if I needed 150, I need 150 there. But if I add them together, guess what? I'm just working backwards. I need 225 plus 150, whatever that is. And then I come over here, and maybe the 180 will come over. I've got to have more. And then I dump off some here, so I'm working back. I know how much the CFM is and this whole thing. The new engineer says, oh, I'll tell you what we'll do. We'll have the diameter of this duct, it'll start out at 20 inches, and then it'll go to 19 inches, and then it'll go to 18 inches, then it'll go to 17 inches, and don't ever design something like that. There's too many step downs, too much crap on the construction site. They just need a couple sizes, and they're going to run it, and then change it, and then run it and be done with it. Anyway, you don't be too tricky in your design to optimize. You just, have a few parts and make it transition. But you then size all of these. Well, what's the criteria? Once you have the layout for a supply, what's the criteria by which you're sizing these? Well, you want to have a reasonable fan back here that's only going to generate so much PSI, or not even PSI, inches of water column pressure to push it through the system. So let's press forward here because I'm going to touch more on that. So the CFM going down the duct that you just are trying to push it through, okay, I need this much CFM. I'm going to get this many feet per minute if I select this duct size. And from Bernoulli's equation, I know that when it speeds up, the pressure drops. When it slows down, the static pressure regain. And then I have some pressure loss. What are the pressure loss equations? Well, you can write them three ways, can't you? It's just like in water systems. A lot of times they'll say something like the velocity pressure is equal to the air density that you're moving in the duct system, velocity in feet per minute divided by 1097 squared, 0.075 pound mass per cubic foot. And this is a constant. such that when you give the velocity in feet per minute, you get a velocity pressure in inches water column. So in air systems, we have inches of water column are often. They call it the velocity pressure. You could also call it the head with a symbol, different symbol, but in air systems, it's velocity pressure. This pressure is as if I had a little manometer hooked up to it, and I measured the column of water that would be pushed up, right? We should be able to reestablish this type of equation. Well, you could use this equation if the density is off from 0.075, which is standard value for standard air, 68 or 70 degrees F, 1 ATM, 50% relative humidity. Or you can just collapse that row of air into it. And this is an equation that is nice to know. It's easy to use. So you have the velocity pressure. That's the gain in the pressure if I bring it to rest at the end of a tip of a pitot tube. That's really what it is, isn't it? That's the velocity pressure, is equal to the velocity in feet per minute divided by 4,005 quantity squared. So think about this. I have a duct. If I have the airflow at 4,005 feet per minute, and that's hauling, that's pretty good. Yeah, that's a pretty high speed. And I bring it to rest at the tip of a pitot tube, what is the pressure gain compared to the static pressure? If I had this hooked up to a manometer and it measured the static pressure on the sidewall and then the pressure at the tip of the pitot tube, the water, if I put water in here, if it's not flowing, it would have the same elevation. If it's flowing, this side goes up, this side goes down. That difference is the H. And it'll measure, if it's flowing at 4,000 feet per minute, it'll measure 1 inch of water column difference, won't it? Yes or no? All right. A lot of residential duct systems, you don't want to go over 1,000 feet per minute because of what you can hear. You can sometimes hear air rushing through ductwork. If we're real quiet taking an exam in some classrooms around here, you can hear it, right? If in my office I'm quiet, I can hear it. I can hear maybe the fan and the computer running, fan up at the projector running, but it's noise, unwanted. Anybody been in a house and they really are annoyed by that? The air conditioning system's running, they're trying to sleep? Yeah. And so I've learned a lot of times that you keep it low and you keep it at 1,000. Well, if it's 1,000 and you divide by 4,000, then you square it. What's the max dynamic pressure or velocity pressure of flowing air in your residential?
16.
Not much, is it? A 1/16 of an inch of water column. So a lot of times in low velocity systems, we know that that's true, but we very rarely does it be converted back to pressure. It's like that form of the energy, the mechanical energy, we're just going to say, yeah, it's there, but we're not going to worry too much about it, energy balance. All right. Anyway, so this are what I just said about inches of water column, that is in feet per minute, and the density of air is this much. Well, why in the air systems, air conditioning systems, if you haven't been emphasized before, why do they treat them always as incompressible? I learned air is compressible, especially in thermodynamics, right? We beat the students up, said liquids are incompressible, but it's a bad approximation for air, ideal gases. But the air in these systems undergoes such a small pressure variation that they're treated as incompressible. Well, what's the consequence of that? We conserve volumetric flow rate. Our continuity equation is simply boils down to a continuity. What happens when you take flow and converge it to a smaller diameter duct, smaller cross-sectional area? It speeds up. And because it speeds up, the velocity pressure went up. If you had conservation of energy, what happens to the static pressure? Down. It's a Venturi effect. Don't forget it. All right. When do we have to consider the compressibility of the air or the density of air changing? Well, the density of air changes when the temperature changes. We don't have a lot of pressure changes to change it, but we do have temperature changes. And likewise, humidity. So the relative humidity. What happens if I move to a high altitude? I want to move to Colorado and I want to do HVAC work in Colorado. Don't use things at sea level like you're doing the work in Corpus or Houston. That's sea level. But if you're going to work up there, look it up. They have different tables. They have different computer codes. You have to put in the altitude that you're at. And if you're especially high and low temperatures, take it into account. But a lot of stuff, where temperature variation's not that much and the density is constant. So you remember that the total pressure is a combination of the static pressure and the velocity pressure. And this pressure, I encourage you to think about pressure as an energy per unit what? Energy per unit, first day almost of the class. What was the concept of pressure? Energy per unit volume. That's exactly right. So some sort of mechanical energy per unit volume of your fluid. It works for liquids, it works for gases, air. Now, if you'll talk, sometimes they have a design method and they'll talk about the static pressure regain or the pressure, the static regain method for design. This is only for fast systems when the velocity pressure is appreciable. A lot of times we're in low velocity systems. When do you have a high velocity system? When you're far away from noise sensitive areas, or you can insulate it from the noise, and you just need to move a lot of air to get from here to there. So in this building, there's some main ducts that may go between floors that have some pretty high velocities. What's the friction loss in a straight run of a pipe? Well, what was it for a straight run of a liquid water pipe? How about it's just like that for a duct. What's this F? Friction factor. What's L over D? And what's this V squared over 2G? It is the same as our velocity pressure. V squared over 2G. And that's our pressure loss. You know what? I think I typed that wrong, didn't I? This needs to be 1/2 rho V squared. Sorry, I put it in as if it was as if it was head that way. So this is 1/2 rho V squared. But that's your velocity pressure, and a lot of times you use this simple equation because you're talking feet per minute for the speed, and you're talking the velocity pressure in inches of water column. That friction factor, could you get it off a Moody diagram just like for the water system? It's now just air through a duct. Yeah. Could it have a laminar region? Yeah, but we don't have very many laminar airflow systems. Okay. Could you have a fully turbulent region? In your mind, you have that Moody diagram. Then we have that on an exam. And we said out here, it's laminar. Out here, it's fully turbulent. And in here, the friction factor is a function of both the relative roughness as well as the Reynolds number. True? And so, yes, often we're in that transition region in air systems, so most of the airflow is done in that region. It's a function of the relative roughness and the velocity. Well, what would be roughness that you see? Well, if you're running in a galvanized sheet metal duct that has joint spacing, so often the common value is thrown out to be the roughness of 0.0003 foot. What about ductboard? That's that. Does anybody know what I mean by ductboard? It's like an insulation. It's a little rougher. You almost have to see it. Yeah, a lot higher than a galvanized sheet metal. What about the spiral inside of flex? it's even worse. Yeah, it's higher. But a lot of people will put together a plot like this. This is from ASHRAE. It's a friction chart. I'm sorry that it's hard to see, but what's on the x-axis? CFM. So it's airflow. Let's say I needed to dump 100 CFM in a room. Then I'm interested in what's happening down here. I need to move 1,000 CFM. I'm interested in what's happening along that line. Now, what about the y-axis? What is this? That's your straight run friction loss. And so this is very interesting. Can you see the units on that straight run friction loss? It's inches of water column per 100 foot of run. So it's like, okay, if I have 100 foot of run, then this is, and I'm running at this CFM in that pipe, or duct, I'd say duct. I need to now, there's some more information on here, but I have to find out the diameter. What do they have? Can you see the diameter? Here it is. That's your duct diameter, isn't it? Sloped that way. So what is this? Can you pick out one or two of these? I know this is a ridiculous duct diameter, but what is this number right here? 100. Give me a reasonable. Give me a 12-inch duct diameter right there, that line. Isn't that 12 inches? So, if somebody said, I want you to push 100 CFM through a 12-inch duct diameter, round, galvanized with that standard roughness, what's going to be the frictional loss in it? Going to be so low, you've got the wrong size diameter. It's going to be intersecting way down here off the chart, right? You could push 1,000 CFM through 12 inch. It would come up right here. That's where you intersect, and it's going to cost 0.2. That'll be the friction loss. 0.2 inches of water column per 100 foot. See how you use that? This is only good for that roughness, round, standard, galvanized. How do they adjust? Well, they put another plot like this for different configuration. Why do they have this shaded region? What do you think? That's where you want to be. If you're out of that shaded region, you might want to ask yourself why. And you can see that right away, that if I'm running a 12-inch diameter duct and all I'm doing is pushing through 300 CFM, that's really probably not economical. I should probably reduce it to maybe a 10-inch. That would move me up here. Could reduce it to an 8-inch. That would move me up here. More reasonable. If you get outside, you have too high of a loss. You're paying too much to push it. They also show you the feet per minute, right? Here is 700 foot per minute, 1,000 foot per minute. You don't want over 1,000 foot per minute in your home. So a lot of times the home is really taking up, it's kind of zoned right in here. There's your home calculations. You don't want it to go faster. Commercial calculations would be outside of that zone. And this is one of those numbers. You remember what Frank mentioned, the standard pressure drop? 0.08. 0.08 inches per 100 foot. That's a good rule of thumb for design. It's not going to cost much, and it's going to be effective at moving the fluid, the air through the system. You can always find recommendations on velocities. So that's why I pick 1,000 for residents. And you get closer to the discharge into the room or the bedroom, it needs to be a little slower. You can have high velocity systems, but first time I saw this chart, it's like, oh yeah, let's put a design point up in here. Oh, forget it. No. It's going to be too high, too fast, too loud. Again, there's lots of recommendations. Did I cover what I wanted to cover back here? Yeah. How many times is it not round? A lot of times it's a large oval. Round is efficient, but sometimes it won't fit in the headspace, and so they'll put an oval if they need more cross-sectional area like that, or they'll put a rectangle. And usually the width is a lot larger than the height on a rectangle. And so you can get the equivalent of, for a rectangular duct, for a round duct equivalent. There's some interesting terms when you do air systems. They'll talk about the friction loss, and then they'll talk about a dynamic loss. What? What's dynamic loss mean? Well, it's a loss that's not in the straight run of the duct. Well, the dynamic loss is due to you're putting it and you turn a corner. Well, what's going to happen when you turn a corner? You get a flow separation. That adds the loss. They don't use that term in the water systems, but they'll use that term in the air systems, that it's a dynamic loss. It's due to especially flow separation, recirculation, dynamic effects. All right. What would you say is equivalent in the water system? Just minor losses due to fittings. This is one that I really wanted to talk about when Frank was mentioning it in his talk. System effects. This is a unique phrase. Did you catch it when he mentioned it? And so what does that come into be? Well, they test a piece of equipment. Maybe they test this element right here, okay? And how do they test it to give you its characteristic for losses? They test it with a straight run and they put it right there. And it's nice developed flow, but often you have a device and another device, and so the input to this device isn't the standard input to it. So because two components are close together, they have an additional effect of loss. And this can be substantial. At first you wouldn't think it, but even if you listen to Frank, I know he mentioned it, that it's like, don't forget to consider your system losses, because they can bite you. They can, as a design engineer. So I'm going to spend just a little bit on this. So you have a bend before a fan. That's a key thing to look out for. Or a bend in the ducts right after the fan outlet. Something to really look for. Or two bends close together, or just an obstruction close to something that's not supposed to have an obstruction. So if you had, let's say, this by itself with the super long run, both in and out, and then the other one by itself, you would say that the pressure, the loss would be, or the pressure loss would be a constant times the velocity pressure right here. And that constant is for that loss coefficient. And you would add it for the first one, you would add it for the second one, velocity. But if they're close enough together, you put a special multiplier right here. That's that K. It's a function of L over D for these two fittings, okay? So this is the L, this distance between the two fittings, and then D is the diameter. Well, when does this K go to unity? Such that there wouldn't be an additional system loss because they're close together. Because if K is 1, then it's just, you're just summing the loss from the first component and the loss from the second component. Well, it's when L over D is greater than 10. They're far enough apart. But if the L over D is 2, look at that system, it's 1.75. You have an additional 75% that you don't want to unaccount for. You want to account for it in the design. Does that make sense how they showing you this system loss effect? So like here again, if far enough away, L over D is 10 or more, system loss effect is 1, forget about it. But if it's close, it can be 1.5 or different values. Where does it really come into play is when you have fan systems. This is one of the manufacturers of fan systems, Greenheck, and this was just a good piece of literature. So I'm going to just kind of scroll through it fast to show you what we're talking about. Let's say that you have a roof and you're exhausting here, and that is the way that that device is tested on a roof that's flat, straight run to it. But you didn't install it that way or design it to be installed that way. You have to come and do a 90-degree turn and then install. Well, you have a lot lower, poorer performance because of the system effect. Or what do you have here? You have a damper that's put there. That's not the way they tested it. But you can't just say damper by itself and then that exhaust by itself. They're too close. There's a system effect which amplifies and has greater head loss. And if you have that damper with the turn like that, you can have significant. Here's one that makes sense. You had a bend right before you had that axial fan. Where what did they do when they tested it? It was straight run, axial fan, straight run. Or here's the easy one. You have it exhausting and there's a wall right there instead of just open to a large space. So these are more common than you might expect. Here's a big one. So you have a centrifugal fan. It's sucking in air in the eye region, turning it and blowing it out that way. But let's say you need to move it upstairs, and so you hook it up this way. Well, the blast area from that fan coming out is high on the top, on that outside, and then you're trying to turn it just the opposite way to go up. It's going to have a significant poor system effect for this case right here, 8A. It's a lot better if you would install it by turning it around such that the blast area is a high speed right here and it's going to go along that wall and then move it up. A lot lower system effect. I'm just kind of exposing you to something that was important and then should have spent more time in the semester, but hey, we got one. We're finishing up here. You can have a system effect if you just discharge it without having a little ductwork on it. How important can those system effects be for loss coefficients? Oh, this is what they're talking about, the blast area. When it comes quite out, right off of that fan, if you cut it right here, it's not a nice profile like this. It has because of the centrifugal nature of the fan, a high speed at the top of that out duct area. Let's jump back here. You may find that the fan wasn't planned to be installed, or the manufacturer shows you its ratings and curves, tested in a really tight room next to another fan. And you can get the system effects to start to be significant amplifiers. Here's one that if you put the outlet to discharge, you might think, oh, I need to turn it this way, right? Or I need to turn it down, or I need to turn it up, or I need to turn it that way. Just look at the amplification. First of all, if you get it far enough away before you turn it, there's no additional loss, but you can have significantly large numbers if it's really, really tight. I didn't have room in that mechanical room. I had to take it off the fan, turn it, and start moving it in a different direction. And they can dominate. Well, the last slide that I want to talk about, and I know that I didn't give you a complete coverage of air system design, but in the time that we have, again, this is the most popular method, easy to use. It's not necessarily the most robust, but equal friction factor method. And so what you do is you try to get every section of the run to have the equal friction factor of 0.08 inches of water column per 100 foot of run, and size it that way. If you ever see the static regain, what they're doing is saying, you know, I think I have it fast enough that I'm going to have significant amount of energy in the velocity pressure. And just like Venturi effect, think about Bernoulli's, it speeds up, the pressure goes down. You slow it down, the pressure builds back up. That part of the component's going to be taken into account. For residences and a lot of applications where you're 1,000 foot per minute or lower, you don't have a lot of potential to regain pressure anyway, so that's not used. Fan selection. So a lot of the fan curves look a lot like the pump curves. Typically they're a little more complex in this region. Stay away, right? And so you want to be out in this sweet spot for the fan operation. You couple the fan with some system, And it's just like water systems, find the operating point. And then what are the affinity laws for the pumps and what are the affinity laws for the fan? What do you want to change often with a fan? Don't you want to change the speed? Usually you're not changing the diameter, but often the speed. And how does changes in the speed affect the performance? What are the key performance metrics or measures for a fan? 3 things. The volumetric flow rate, the flow rate. What's the next one? What would be the next one? Just like in water systems. It'll be how much energy the fan was successful to push into the fluid stream. That's usually measured in energy per unit volume. That would be maybe pressure gain across the fan. So if you're looking at this fan curve right here, they're plotting the volumetric flow rate, CFM, versus what on this y-axis? Some pressure gain, isn't it? And then what's the third metric? Some brake horsepower. I'm going to have to feed a shaft that's going to have to continually feed mechanical power to that fan. And so it's the same thing with the pump systems. And so they'll be like that. So how does the volumetric flow rate vary if I start changing the speed? What is the affinity law, the relationship between Q and N for a fan? It would be proportional. True? It's a centrifugal fan. It's throwing it off the tips of the blades. What is the relationship between the pressure gain in the fan and the speed of the fan? You can guess, right? N to the what power? Squared. And then the brake horsepower? N cubed. I hadn't planned on covering new information today, but I felt that I did you injustice by not at least talking a little bit more about air system design. As you look for 1 week from now to take the final exam, you should anticipate air system, fan, some type of problem. Water system, pump, some type of problem, that's 2. Uncertainty analysis, 3. And the other one? Modest heat exchanger problem, not the complicated compact. You've been a good class. Thank you for your attention. And I like to see you dressed up on my last day of lecture. Thank you so much.